and welcome to the Coffee with the Professor. My name is Milica Todorovic. I am a physicist and a computational material scientist, and from the 1st of June in 2021 I will be the assistant professor at the newly founded Department of Mechanical and Materials Engineering at the University of Turku. Today I will tell you a little bit about my own research area, which is artificial intelligence in computational material science research. I will start this talk by introducing you to computational material science, and then I will explain how to use AI in this research. I will recount a couple of examples of AI applications, and then tell you how we can use AI for materials design. So let's start with computational material science. In my research field, we are primarily interested in functional materials, and these can be very, very different types. So from small molecules that absorb and emit light, which we use in LED technologies, to complex metallic alloys for phase change materials, which we have in mobile phone memories, to wood-derived biofuels like cellulose, and also some exotic organic and inorganic perovskite materials for next-generation solar cells. So as computational material scientists, we use simulations to study the structure and properties of these materials, and our objective is to optimize the functional properties of materials and their performance in devices. So how do we do these investigations? We use various simulation methods, and this is a little bit complicated in computational material science because our systems span different kinds of length scales. We start from picometers, which is 10 to the minus 12 meters, all the way up to the meters. So at different length scales, we use different simulation methods. Between picometers and nanometers, we are in the realm of quantum physics, and we use quantum mechanical, highly accurate simulation methods like wave function tools or density functional theory. And we're interested in computing electronic structure of the materials, like electronic levels in materials, band gaps, and similar. And this is the realm of quantum physics and quantum chemistry. Between nanometers and micrometers, we don't worry much about electrons. We are mostly interested in modeling atoms. So we use atomistic simulation methods like semi-empirical, tight binding methods, or force field methods. And this is mostly the realm of chemistry. When we get to microstructures, and this is the realm of nanotechnology, we talk about quantum dots and micrographs. Here we use a lot of rate equation modeling and continuum models. And when we get to millimeters to meters, this is now the length scale of real devices and maybe the domain of engineering. And here we use a lot of finite element modeling. So in all of these simulations, we have some similar objectives. Our primary objective is to understand the internal structure of the material, and that is the natural arrangement of atoms inside the material, which minimizes the internal energy of the material, and we call this the natural state of matter. So here's an example of silicon. So you see here a chunk of silicon that's inside our mobile phone and computer chips. And if you zoom in on the atomistic structure, you see it's got a regular lattice. And if you zoom in to the smallest repeatable component, that is the unit cell of silicon, and this is what we call the natural state of silicon. So once we find out the internal structure, we're interested in finding a lot of functional properties of materials, and these can be of different types. They can be structural, like hardness or elasticity. They can be electrical, like charge mobility or conductivity. There's magnetic properties, like magnetic moment or permeability. And of course, spectral response, so various kind of response to radiation. And the idea is that function of materials, functional properties depend critically on the internal structure. So if we know the internal structure, we know the functional properties, and if we change the internal structure, we can also change the functional property, which allows us to do materials engineering. So materials engineering, like alloying, has been done since the Bronze Age, like for a very, very long time. But nowadays, modern material science does a lot of sophisticated doping to the point where we put together different kinds of materials in complex heterostructures, which overall have functional properties that are very different from the ingredient compounds. And this leads us to the objectives of materials design. Ideally, we would like to find what kind of materials we could discover that might perform even better in the devices and technologies we currently have. And the material science objectives in computation have evolved a little bit because the paradigm of how we do science has evolved over time. So as I mentioned, experimental science has been done ever since the dawn of time. And it was relatively recently on this time scale that we started realizing that we can encode the laws of nature into theories and use theories to describe our world. And it wasn't really until a couple of centuries ago, in the time of Newton and Maxwell and Einstein, that we could reliably do theoretical science. And then in the 50s and 60s of the 20th century came computers and supercomputers, but it wasn't really until the 90s that we really were able to get large enough supercomputers to generate a large amount of computational science. And then people realized that a lot of computational results were constantly being recomputed instead of being pooled together and stored. And in the kind of 2000s, we realized that we suddenly had storage capabilities to pool data, and we had the network bandwidth to reliably upload, download, and stream data. And this led to the advent of data-driven science. And data-driven science was directly promoted by the establishment of materials data infrastructures. And here you can see a map of different data infrastructures in the world, and the color denotes the time at which, or the year at which they were established. And so you can see that before 2000s, nothing really was happening. And then after 2000s, it was the establishment of AFLOW and the Materials Project in the US, which really opened up the floodgates to materials data infrastructures. And the US continues to lead in this field ever since. In 2015, Europe got its biggest materials infrastructures, and Finland also participated in the establishment of the Nomad data repository based in Germany. So with this data infrastructure, it suddenly became possible to curate very, very large material science data sets and then apply AI and machine learning methods to these data sets. So here is a typical workflow or a protocol of how we might apply AI to data from material science. We have to start with a data set, so that's a constant, but we can't put the data set itself into a machine learning algorithm. We have to first design a representation, which is a way of encoding the data set into a digital form that the AI algorithm will understand and interpret. So once we've encoded our representations, then we choose a suitable machine learning method out of many available ones. And after we've obtained our results, we have to do quite a bit of quality control. And this usually involves going back in the workflow to check if there was a representation that might have performed better, or a machine learning method that might have been more suitable for this work. And this is what we teach our students when they come to the Machine Learning for Material Science course, which we've been running for 4 years now in the Helsinki area, and it will start this fall in Turku. So now that we had the data science down, and we had the data sets, and we had the AI algorithms, I want to discuss with you some typical objectives of the research studies when we apply AI in material science. So one major objective was to replace or accelerate costly calculations. So these quantum mechanical calculations, we always want to do them. They're highly accurate, but they're very computationally costly. And so people have realized that they can replace the entire calculation by training interatomic potentials with machine learning, and they can get then quantum mechanical level accuracy in a fraction of time. Another cool application is to take quantum mechanical data and to train an AI method on a lot of quantum mechanical data until the AI learns how to mimic the quantum mechanical calculation itself. And then we can just bypass the calculation and just use the AI model for fast prediction. And this kind of fast predictions with trained AI models lead us to AI-driven materials screening. So here is where we use AI to train to map structure to property or property to structure in materials. And we can use these kinds of pre-trained AI models to do screening of vast amount of materials for potential functional applications. And the last objective is materials optimization and design. And this is a slightly more advanced objective with models like active learning, generative models, and automated experimentation. So let me introduce you to AI for materials pre-screening. This is done very frequently, and it's a very powerful technique. So to begin with, we need to have a data set. If we want to map a structure of a material like the molecule to some kind of functional property, let's say energy here, we need to have a lot of input-output pairs. That's structure and property pairs. And this constitutes our data set. And the data set can be can be obtained from a database or computed or obtained from experiment. So with this data set of input-output pairs, we then train a machine learning model. And this trained AI model then becomes a resource. After the model is trained and has good predictive accuracy, we can input any previously unseen molecular structure, and the AI should instantly predict what is the associated functional property. And this is enormously useful because now you can take millions of untested molecules, put them through the AI predictor model, and find out which molecules or which groups of molecules have advantageous functional properties, so you can then try them out in experiments. So in my own group, we have done similar applications. We wanted to map the structure of small molecules to some functional property. And here we were first interested in the electronic levels in materials, the energies of the electronic levels in these molecules. And this is related to the way the molecules absorb or emit light. So we trained a model called kernel ridge regression to map from molecule structure to the electronic levels. And this worked really well and had good predictive accuracy. Then we went a step further and we trained a neural network model to map molecule structure to an entire optical spectrum of the molecule. And this also works surprisingly well, even though it was a more difficult AI learning task. And in fact, Samsung called us up about this neural network model. They are constantly screening small molecules for their LED television technologies. And they were looking for pre-trained model like our neural network to help them in this screening process. So this pre-screening really has industrial applications. So one problem with the pre-screening application is that you need a large amount of data to help you train the model reliably. And this is sometimes difficult to obtain. One way to get around this is to use active learning. Active learning is a machine learning procedure where the AI itself observes a lot of atomic structures and the related properties, and at the same time it learns and predicts which structures have the optimal properties. So this movie shows that AI is observing the conformers of a small molecule called alanine and predicting which conformer might have the lowest internal energy and therefore is the one that exists in nature. This problem is called a conformer search, and it's particularly relevant for drug discovery, where it has been found that the forms of molecules that are favored in nature actually are not always medically active. So it's important to keep in mind what is the form that is naturally found. An interesting aspect of active learning is that the model simultaneously trains and predicts. So these two actions happen at the same time. And this is different in classical machine learning, where you first train the model, and then after finishing training, you do the prediction. Another interesting aspect of active learning is that the AI itself chooses which data points it will include in the data set. And this is different in the classical machine learning, where usually humans curate the data sets. And it turns out that the AI is more efficient at curating good data sets than humans. And that is because it has mathematical acquisition functions that decide where you can get the most informative data. So it tends to search the region that is already promising for potentially better solutions, but it also tends to search regions where there's not many data already in the case that it finds an even better solution there. And these strategies are so efficient that the AI can learn quite well from a smaller quantity of data. And these data efficient approaches means that they're good for costly calculations and also for experimental work. We liked active learning so much that we encoded it into our own Bayesian optimization code for use in materials research. And the code is called Bayesian Optimization Structure Search. It has these three components. The AI engine is Bayesian Optimization, which is a classic tool in computer science for complex optimization. And this tool allows us to build surrogate models for the properties of materials. And then after we convert the surrogate models, we can read off the optimal solutions as minima, maxima, and even barriers between them. The data has to come from somewhere. Usually we take total energy simulations from supercomputers, but it can also be from experiments. And in computational work, we tend to make an approximation to keep some parts of the molecule rigid, and this is called a building block approximation. So all these three components make up BOSS, and BOSS is a code that is free to use and publicly available. Here's an example where we used BOSS to infer the optimal adsorption geometry for a complex molecule on a surface. So here we have C60 on titanium dioxide anatase. These are both industrial materials often used in solar cells. And you can see in the movie on the right that the boss is looking at different configurations of the material, and on the right, at the same time, it's doing a prediction of what would be the most energetically favorable adsorption geometry. And so understanding the contact between these two materials is incredibly useful to understanding interfaces in solar cell devices and the properties of devices. Since then, we have used BOSS for several different materials research problems. With our colleagues in Austria, we've looked into the structure and properties of organic thin films. In this case, it's TCNE on a copper surface. And we established that the first layer of TCNE forms vertically to the surface, and then the next layer absorbs on top of that, absorbs horizontally. And this kind of structural identification is really important for understanding how far the charge transfer goes from the inorganic to the organic film. In collaboration with my colleague at Aalto, Shi Chen, we are looking at ligand-protecting nanoparticles, and these have very complicated structures, so structure search is one way of understanding how these particles behave in health technologies and health applications. Now, Bayesian optimization has been so data efficient that we started wondering how we can use it to optimize experimental outcomes. So we were wondering if we can tune the processing conditions of experiments just to achieve an optimal outcome without understanding anything that occurs in the middle. And we decided to try this and to engineer a particle morphology between 1D shapes and 3D shapes. So this was a collaboration with chemical engineers, and we used a bio-derived material called oxidized tannic acid, which tends to form supramolecular complexes. And we put it in a solution where we could vary two design components, pH and pKa. And we generated several types of particles. We quantified their morphology. We put it into the BOSS model. And we got out a morphology map that tells us how the particle morphology varies in the design space of pH and pKa. And this told us that if we use high pKa and pH values, we obtain predominantly 1D particles, and opposite, if we use low pKa and low pH, it's mostly 3D. And you can get anything in between. So then we looked at some SEM images that they obtained for their particles, and it was really true. The predictions of the AI model really followed the experimental outcomes. And this got us very excited, and now we're looking at different ways to use active learning on experimental data. Okay, so I'd like to stop and summarize here. What I just described represents the advances from the past 5 to 10 years, so this is a very young research field, and we have only scratched the surface in what AI methods can do for us. So there's a lot of hot new methods coming up, and I'd like to tell you about what's coming up next. So first is multi-objective materials design. Up until now, we have mostly used materials design with respect to one functional property, but in reality, from every data point, whether computational or experimental, we often obtain multiple functional properties at the same time. So it would be really good to do AI in ways that allows us to obtain low energy structures that are commonly found in nature, but also have a certain elasticity property or adsorb at a certain wavelength or any kind of specification that comes from the technological needs. Another interesting application is inverse prediction of for materials discovery. Materials discovery has often been done by mapping structure to property, but in real applications, we often want to start with a property, for example, that the material adsorbs at a certain wavelength, and then infer what kind of structure produces that. And this kind of predictive task is very complicated and relies on accurate generative models, and there's a lot of work now to improve generative models so that they really suggest synthesizable materials. Another interesting method coming up is multi-fidelity learning, where we study the same process with data points of different type of accuracy. And it turns out that AI can learn very efficiently from a lot of data that is cheap to compute or obtain but not very accurate, and then just refine the predictions with a small number of data points from an accurate method. This is much more efficient than classical machine learning, and there's a lot of research into this now. The next item, automated experimentation platforms, is closely related to using active learning to guide experiments. As I said before, active learning has powerful acquisition functions capable of picking the most informative data points, And this means that AI can guide experiment better than the trial and error procedures we currently do in experimental work. Unfortunately, employing active learning with human-based experimentation is very complex, and this works much, much better if the entire experiment is fully automated. That is to say, both the fabrication and the characterization is automated. There are only a handful of automated experimentation platforms available globally, but at Turku University, in our department, we have just applied to the Academy of Finland for funding to build such a platform. And if it all goes well, maybe this time next year, we will have such a platform available also in the Turku region. And lastly, in the very last 2 years, maybe the natural language processing techniques have made huge advances in understanding literature and speech. And it's very exciting to consider how much new knowledge can be generated by applying natural language processing to scientific texts. Okay, so this is where I'd like to stop and summarize my talk. AI is fast becoming a standard tool in materials research. It can be used both with computational and experimental data, but I have to say we don't understand yet so well how to use it with experimental data. So I would like to encourage our industrial partners, if they have any data sets or would like to apply AI in their work, it would be really interesting to collaborate and to explore how to best apply AI for scientific discovery. It's good to keep in mind that AI is mostly used for pre-screening purposes or material optimization. Before I stop, I'd like to acknowledge some of my colleagues who helped me in this work. Our students in my group at Aalto University have been fantastic in applying these tools from computer science and transferring them to physics. I'd like to thank my collaborators, both from physics and from computer science, and acknowledge that there were 3 institutions that were mainly supporting this work. We work closely with the Finnish Center for AI, in particular highlight the AI-driven design of materials. We work a lot with the CSC, the National Supercomputer, where I'm currently running a Mahdi Grand Challenge project. And we've been supporting for some time already by the Academy of Finland through its AI in Physical Sciences project. Thank you very much.